Let me tell you something strange. Right now, as you're lying there, maybe pulling the covers up, settling in for the night, every single atom in your body is doing something that would have baffled the greatest minds in science for most of human history. Inside each of those atoms, there are particles, tiny little specks of matter, and not a single one of them has a definite position. Not one. They're not sitting still somewhere, waiting to be found. They're not orbiting in neat little circles. They're sort of everywhere and nowhere at the same time, smeared out across space, in a haze of possibilities. And here's the thing. It's not that we haven't built a good enough microscope. It's not that our instruments are too clumsy, or that we're missing some crucial piece of technology. The particle genuinely does not have an exact location. It's not hiding. It's not being coy. The universe simply does not assign it a precise address. And that might sound like a flaw, like nature left something unfinished, like there's a glitch in the operating system of reality. But it's not a flaw. It's a feature. In fact, if particles did have exact positions, if everything in the subatomic world behaved the way our everyday intuition says it should, then atoms would collapse, chemistry would be impossible, stars would never shine, and you and I, and everything we've ever known, would simply not exist. The uncertainty isn't a limitation. It's the reason there's a universe at all. So tonight, I want to take you on a journey into one of the deepest and most beautiful ideas in all of physics. The idea that there are things about nature that are not just unknown, but genuinely unknowable. Not because we're not smart enough, not because we need better equipment, but because that's how reality actually works at its most fundamental level. And I want to show you why that's not just okay, but actually wonderful. Why the fuzziness at the heart of nature is what makes everything possible. Let's start somewhere comfortable. Let's start with the world as it seems. You throw a ball, and it follows a nice, clean arc through the air. You can predict exactly where it's going to land. You know how fast it's moving. You know its position at every instant. If someone gave you the right equations and a good stopwatch, you could track that ball's entire journey from the moment it left your hand to the moment it hit the ground. Nothing mysterious about it. That's the world Isaac Newton gave us, back in the late 1600s. A world of certainty. A world where, if you knew the position and velocity of every particle in the universe at one single moment, you could, in principle, calculate the entire future. Every raindrop, every heartbeat, every star going supernova, all of it just the inevitable consequence of where everything was and how fast it was moving at some earlier moment. This was an incredibly powerful idea, and for about 200 years it worked beautifully. Newton's mechanics sent cannonballs on predictable trajectories. It explained the orbits of planets. It told engineers how to build bridges and predict tides. The universe was a clock, intricate and beautiful. And if you understood the gears, you understood everything. There was a French mathematician named Pierre-Simon Laplace who captured this idea perfectly. He imagined a vast intellect, what we now call Laplace's demon, that knew the position and momentum of every single particle in the universe. For such an intellect, Laplace said, nothing would be uncertain. The future and the past would be equally clear. No surprises, no mystery, just mathematics unfolding like a scroll. And for a long time, nobody had much reason to doubt this picture. Sure, in practice, you could never know the position and velocity of every particle. That would be absurd. But in principle, the information was there. The world was deterministic, which is a fancy way of saying that if you could somehow rewind the universe to any earlier moment and let it play forward again, everything would happen exactly the same way. the same stars would form. The same planets would coalesce. The same dinosaurs would roam the same forests. The same you would be lying in the same bed, listening to the same story. Nothing was left to chance. Randomness was just a word for things we hadn't figured out yet. Makes sense, right? It matches our everyday experience pretty well. When you set a cup on a table, it stays where you put it. When you drop your keys, they fall straight down. The world feels solid, predictable, knowable. And that intuition served humanity well for centuries. But then, something happened. Toward the end of the 1800s, physicists started poking at the very small, not baseballs and planets, but atoms, electrons, light itself. And when they looked closely enough, the clockwork started to stutter. Little glitches appeared, tiny contradictions, experiments that gave results that made no sense under the old rules. And slowly, painfully, a completely new picture of reality began to emerge. A picture so strange that some of the smartest people who ever lived spent decades arguing about what it meant. A picture where certainty wasn't just hard to achieve, it was fundamentally impossible. Where particles didn't have exact positions, where measuring one thing about a particle necessarily blurred another, where the very act of asking a question about nature changed the answer you got. This is the world of quantum mechanics, and at its heart sits something called the uncertainty principle. It's one of the most misunderstood ideas in all of science, and also one of the most profound. And the story of how we got there, how we went from Newton's clockwork to Heisenberg's uncertainty, is one of the great intellectual adventures in human history. So let's go back. Let's start with light, because that's where the trouble began. By the late 1800s, physicists thought they had light pretty well figured out. James Clerk Maxwell, a Scottish physicist with one of the most extraordinary minds in the history of science, had shown in the 1860s that light was an electromagnetic wave, a ripple in electric and magnetic fields, oscillating perpendicular to each other, racing through space at about 300,000 kilometers per second. Maxwell's equations were gorgeous, elegant, and they explained everything from radio waves to X-rays to the colors of the rainbow. Light was a wave. Case closed. Except it wasn't. There was this problem. It had to do with hot things glowing. You know how when you heat up a piece of metal, it starts to glow? First a dull red, then orange, then yellow, then eventually white hot. That glow is the metal emitting light, electromagnetic radiation, because of the thermal energy of its vibrating atoms. Now, the physics of the time predicted something very specific about how that radiation should be distributed across different frequencies. And the prediction was catastrophically wrong. It was called the ultraviolet catastrophe. And the name gives you a hint of how bad the problem was. Classical physics predicted that a hot object should emit an infinite amount of energy at high frequencies, in the ultraviolet range and beyond. Infinite energy, just pouring out endlessly. Obviously, that doesn't happen. Your stove doesn't blast you with lethal doses of ultraviolet radiation when you turn it on. So something was deeply wrong with the theory. In the year 1900, a German physicist named Max Planck found a mathematical fix, and he hated it. Planck was a conservative thinker, a man who loved classical physics and didn't want to break it, but the numbers forced his hand. The only way to make the math match the experiments was to assume something radical. Energy, he proposed, wasn't continuous. It didn't flow smoothly like water from a tap. Instead, it came in tiny, discrete packets, little chunks. He called them quanta, from the Latin word for how much. And each quantum of energy was proportional to the frequency of the light, linked by a tiny, tiny number that we now call Planck's constant. Now, Planck's constant is absurdly small. It's about 6.6 times 10 to the minus 34 joule seconds. That number is so small, it's basically invisible in everyday life. You would never notice energy coming in packets when you're boiling water or turning on a lamp. The packets are so tiny that the energy seems perfectly smooth, like how a sandy beach looks solid and continuous, even though it's made of individual grains. But at the atomic scale, where energies are incredibly small, those packets matter. They matter enormously. Planck himself didn't fully appreciate what he'd done. He thought of the quanta as a mathematical trick, a useful fiction that happened to make the equations work. He didn't think energy was actually quantized. He thought there was probably a deeper, classical explanation hiding somewhere, and that someone would eventually find it and restore the smooth, continuous universe he loved. That didn't happen. Instead, 5 years later, a young patent clerk in Bern, Switzerland, took Planck's idea and ran with it in a direction that nobody expected. His name was Albert Einstein, and in 1905, the same year he published his theory of special relativity and his paper on Brownian motion, he wrote another paper that would eventually win him the Nobel Prize. Not relativity, the photoelectric effect. Here's what the photoelectric effect is. You shine light on a metal surface, and sometimes electrons get knocked off. That's it. Simple enough. But the details were baffling. Classical physics said that if you shined brighter light, the electrons should come off with more energy. Makes intuitive sense, right? More light, more energy, harder kick. But that's not what happened. What actually happened was that the energy of the ejected electrons depended on the color of the light, its frequency, not on how bright it was. Bright red light couldn't knock electrons off at all, no matter how intense it was. But a dim beam of blue or ultraviolet light knocked them right off. Einstein explained this by taking Planck's idea seriously, maybe even more seriously than Planck intended. Light, Einstein said, doesn't just interact with matter in discrete packets. Light itself comes in packets, particles of light, each one carrying an energy equal to Planck's constant times the frequency. He called them light quanta, and later they'd be named photons. And this was deeply strange, because Maxwell had proved that light was a wave. The evidence was overwhelming. Interference, diffraction, polarization, all of these are wave phenomena, and light exhibited all of them beautifully. But now Einstein was saying light was also made of particles, not either or, both, somehow. This was the first whisper of a profound strangeness at the heart of quantum physics. The idea that things at the atomic scale don't fit neatly into our everyday categories. Light isn't a wave. Light isn't a particle. It's something else entirely. Something that doesn't have a good analogy in the world you can see and touch. And depending on how you look at it, depending on what experiment you do, it shows you one face or the other. But it's always both, always. Think about that for a second. The light from whatever lamp or screen is near you right now, that light is simultaneously a wave spreading out through space and a stream of tiny particles, each one carrying a definite packet of energy. Both descriptions are true. Neither is complete. And if that feels uncomfortable, if it feels like it shouldn't be possible, well, you're in good company. It bothered some of the greatest physicists of the 20th century too. But nature doesn't care about our comfort. It is what it is. And things were about to get even stranger. Let's talk about atoms. Because by the early 1900s, physicists knew that atoms existed, but they had almost no idea what they looked like inside. The word atom comes from the Greek atomos, meaning uncuttable, indivisible. But by 1900, it was becoming clear that atoms were not indivisible at all. They had internal structure. They had parts. J.J. Thomson, working at the Cavendish Laboratory in Cambridge, England, had discovered the electron in 1897, tiny, negatively charged particles that could be pulled out of atoms. So atoms contained electrons. But atoms are electrically neutral overall, which meant there had to be some positive charge in there too, to balance out the negative electrons. Thomson proposed a model. He imagined the atom as a sort of blob of positive charge, like a pudding, with electrons embedded in it like plums. The plum pudding model. It was a reasonable guess, and it was completely wrong. The man who demolished it was Ernest Rutherford, a New Zealander working in Manchester, one of the great experimentalists in the history of physics. In 1911, Rutherford and his colleagues, Hans Geiger and Ernest Marsden, fired tiny alpha particles, which are essentially the nuclei of helium atoms, at a thin gold foil. If Thomson's pudding model was correct, the alpha particles should have sailed right through, maybe deflecting slightly, like bullets through tissue paper, and most of them did, but some of them, a tiny fraction, bounced back. They came flying back toward the source. Rutherford later said, "It was as if you fired a 15-inch artillery shell at a piece of tissue paper, and it came back and hit you." The only explanation was that almost all of the atom's mass and all of its positive charge was concentrated in a tiny, dense core at the center, the nucleus. And the rest of the atom was mostly empty space, with the electrons orbiting somewhere out there, like planets around a sun, but at vastly greater relative distances. If the nucleus were the size of a marble, the atom as a whole would be the size of a football stadium. That's how empty atoms are. And that means you, right now, lying there, are mostly empty space. The atoms that make up your body are almost entirely nothing. The solid feeling of the mattress beneath you, the weight of the blanket on top of you, it's all electromagnetic forces between atoms, not actual physical contact between solid objects. There's nothing truly solid about any of it. But anyway, Rutherford's model had a problem, a very serious problem, and this is where our story takes a crucial turn. According to classical electromagnetism, Maxwell's equations, an electron orbiting a nucleus should radiate energy. It's an accelerating charged particle, after all, since changing direction counts as acceleration even if the speed stays the same. And accelerating charges emit electromagnetic radiation. That's how antennas work. That's how radio transmitters work. An orbiting electron should be constantly emitting light, losing energy, and spiraling inward toward the nucleus. Quickly, in about 100 trillionth of a second, every atom in the universe should have collapsed. The electrons should have crashed into the nuclei, emitting a burst of radiation, and matter, as we know it, should not exist. Obviously, matter exists. You exist. Something was very wrong with the classical picture. Enter Niels Bohr, a young Danish physicist, tall and quiet and intense, who had gone to Manchester to work with Rutherford. In 1913, Bohr proposed something radical. He said, "What if electrons can't just orbit at any distance from the nucleus? What if they're restricted to certain specific orbits, certain energy levels, and nothing in between? And while they're in one of these allowed orbits, they don't radiate. They just don't. The classical rules don't apply. The electron sits in its orbit, stable and happy, and only when it jumps from one allowed orbit to another does it emit or absorb a photon, a packet of light, with an energy exactly equal to the difference between the two levels." This was audacious. Bohr was essentially saying, the classical rules that work perfectly for everything we can see and touch just stop working inside atoms. He wasn't explaining why they stop working. He was just asserting it, because the alternative was atoms that couldn't exist. And his model worked. It correctly predicted the colors of light emitted by hydrogen atoms, the simplest atom, with just one proton and one electron. The specific wavelengths that hydrogen emits when you heat it up or run electricity through it. Those precise spectral lines that had been measured with extraordinary accuracy. Bohr's model nailed them. The math matched the experiments beautifully. But Bohr's model was also deeply unsatisfying. And Bohr knew it. It was a patchwork. It mixed classical ideas with quantum ones in an ad hoc way. It said electrons could only be in certain orbits, but didn't explain why. It worked for hydrogen, but got increasingly inaccurate for heavier atoms. It was a stepping stone, not the destination. And for the next decade or so, physicists struggled to find something deeper, something that would explain not just what the rules were, but why they were. And during that decade, something else happened that would turn out to be crucial. In 1924, a French physicist named Louis de Broglie, a prince, actually, an aristocrat with a doctoral thesis to write, proposed something that sounded almost absurd. If light, which everyone had thought was a wave, also behaves like a particle, maybe matter, which everyone thought was made of particles, also behaves like a wave. De Broglie suggested that every particle, every electron, every proton, every atom, everything, has an associated wavelength. And that wavelength is inversely proportional to the particle's momentum, Planck's constant, that same tiny number, divided by the momentum. For a baseball or a human body, the wavelength is so fantastically small that it's utterly undetectable. It's billions of times smaller than an atomic nucleus. But for an electron, which has very little mass and can move at modest speeds, the wavelength is on the order of the size of an atom, and that changes everything. Think about what this means. An electron isn't just a tiny dot, it's also a wave. It has a wavelength and a frequency. And if you confine it inside an atom, it has to behave like a wave that's trapped in a small space. Think about a guitar string. When you pluck a guitar string, it doesn't vibrate at just any frequency. It vibrates at specific frequencies, determined by the length of the string and the way it's fastened at both ends. Only certain standing waves fit. Only certain resonant patterns are allowed. The string can vibrate at its fundamental frequency, or at twice that frequency, or 3 times, but not at, say, 2.5 times. The boundary conditions select the allowed waves. De Broglie realized that if electrons are waves, and they're confined within atoms, then only certain wavelengths will fit. Only certain standing wave patterns are possible, and those allowed patterns correspond exactly to Bohr's allowed orbits. The mystery of why electrons can only be in certain orbits suddenly had an answer. They're waves, and only certain waves fit inside the atom. It's the same reason a flute plays specific notes and not every possible pitch. The geometry selects the harmonics. This was a beautiful insight. De Broglie's thesis committee wasn't entirely sure what to make of it. They sent it to Einstein for review. Einstein loved it. He called it a work of genius. And within a few years, experiments confirmed that electrons really do behave like waves. Clinton Davison and Lester Germer, working at Bell Labs in New Jersey in 1927, fired electrons at a nickel crystal and saw diffraction patterns, the telltale signature of wave behavior. Electrons were diffracting, just like light through a narrow slit. De Broglie was right. Matter is waves. And now, finally, we arrive at the heart of our story. Because once you accept that particles are also waves, something very profound follows, something inescapable. something that Werner Heisenberg figured out in 1927 in a burst of creative insight on the tiny island of Helgoland in the North Sea. Let me set the scene, because this matters. Heisenberg was young, just 25 years old, and he was wrestling with one of the deepest problems in physics. He was trying to build a complete mathematical framework for quantum mechanics, one that would replace Bohr's patchwork with something rigorous and self-consistent. And he was struggling. The math was unfamiliar, the concepts were slippery, and the old intuitions kept getting in the way. Heisenberg had gone to Helgoland because he suffered from terrible hay fever, and the island's sea air gave him relief. He was practically alone, working through the nights, scribbling equations, and he had a guiding principle that turned out to be revolutionary. He decided to build his theory only out of things that could actually be observed. Not electron orbits, because nobody had ever seen an electron orbit. Not trajectories, because nobody had ever watched an electron travel along a path. Only things you could actually measure, like the frequencies and intensities of the light that atoms emit. This sounds almost obvious when you say it out loud. Of course you should build your theory on observables, but it was radical, because it meant giving up on the idea that an electron has a definite position at every moment in time. If you can't observe it, Heisenberg said, why assume it exists? And out of this principle, Heisenberg built something extraordinary. A mathematical framework called matrix mechanics, where the physical quantities aren't ordinary numbers, they're matrices, arrays of numbers, and crucially, the order in which you multiply them matters. If you multiply matrix A by matrix B, you don't get the same result as multiplying B by A. In math terms, they don't commute. This might sound like an obscure mathematical detail, but it's not. It's the beating heart of quantum mechanics, and it leads directly to the uncertainty principle. Here's why. In Heisenberg's framework, position and momentum are represented by matrices that don't commute. And when two quantities don't commute, there's a mathematical theorem that says you can't simultaneously know both of them with arbitrary precision. The more precisely you know one, the less precisely you can know the other. It's not a matter of cleverness or technology. It's a mathematical fact, baked into the structure of the theory, which is itself baked into the structure of reality. Heisenberg expressed this as an inequality. The uncertainty in position, multiplied by the uncertainty in momentum, is always greater than or equal to Planck's constant divided by 4 pi. Always. No exceptions. No loopholes. No future technology that could get around it. It's a fundamental limit, built into the fabric of the universe. And I want to be really clear about what this means, because this is where most people get the wrong idea. The uncertainty principle is not about the clumsiness of our measurements. It's not saying that when you try to measure a particle's position, you inevitably disturb its momentum. That's a story that's often told, and it's not entirely wrong as a rough illustration, but it misses the deeper point. The deeper point is this. The particle does not have a definite position and a definite momentum at the same time. It's not that it has both and we just can't find out. It genuinely, objectively, as a matter of physical fact, does not possess both properties simultaneously. The fuzziness is not in our knowledge. The fuzziness is in reality itself. Let that sink in for a moment. Every particle that makes up your body right now, every electron, every quark, every proton and neutron, none of them has a precise location and a precise velocity at this moment. Not because we're not looking, because they don't. They can't. The universe doesn't work that way. And if you're lying there thinking, well, that's weird, but it's just atoms, it doesn't affect me, let me tell you something. It does affect you. It's the reason you exist. But before we get to why, let me back up a little and explain the uncertainty principle from a different angle. Because there's a way to understand it that's actually quite intuitive once you see it. And it comes from thinking about waves. Remember, de Broglie showed that particles are also waves. An electron has a wavelength. A proton has a wavelength. Everything does. And in quantum mechanics, the state of a particle is described by something called a wave function. The wave function tells you the probability of finding the particle at different locations. Where the wave function is large, you're likely to find the particle. Where it's small, you're not. And the wave function evolves over time according to a beautiful equation that Erwin Schrödinger wrote down in 1926. Now, here's the key insight. What does it mean for a wave to have a definite position? Think about it. A wave, by its nature, is spread out. A pure wave, one with a single, definite wavelength, extends infinitely in all directions. It has no beginning and no end. It's everywhere. So a particle with a perfectly definite wavelength, and therefore a perfectly definite momentum, since de Broglie told us wavelength and momentum are linked, is a wave that's spread out over all of space. Its position is completely undefined. It could be anywhere. Now, what if you want to localize the wave? What if you want to create a wave that's concentrated in a small region of space, like a pulse or a blip? You can do that, but only by adding together waves of many different wavelengths. It's like mixing notes on a synthesizer. A pure tone is a single frequency that goes on forever, but a short, sharp click is made up of a huge range of frequencies all added together. The more localized you want the sound, the more frequencies you need to mix. This is a deep mathematical fact, and it has a name. It's called Fourier analysis, named after the French mathematician Jean-Baptiste Joseph Fourier, who figured out in the early 1800s that any wave shape can be built by adding together simple sine waves of different frequencies. And here's the crucial point. There's a trade-off. A wave that's very localized in space, compressed into a tiny region, must be made of a wide spread of wavelengths. And a wave that has a very precise wavelength must be spread out over a large region of space. This isn't quantum mechanics yet. This is just math, just the properties of waves. But apply it to quantum particles, where wavelength equals Planck's constant over momentum, and you get Heisenberg's uncertainty principle directly. A particle with a well-defined position, a tightly localized wave function, must have a large spread of possible momenta. A particle with a well-defined momentum, a wave function with a precise wavelength, must be spread out over a large region of space. You cannot have both at once. It's not a limitation of measurement. It's a property of waves. And since particles are waves, it's a property of particles. This is why I love this explanation. It shows you that the uncertainty principle isn't some weird, mysterious decree from the quantum gods. It's the same trade-off that sound engineers deal with every day. The same reason a short musical note can't have a perfectly defined pitch. The same reason a sharp pulse on a radar screen is made of many frequencies. The uncertainty principle is wave mechanics, and particles, at the deepest level, are waves. Now, let me take a little detour here, because there's a beautiful parallel version of the uncertainty principle that doesn't get talked about as much, and it involves energy and time. Just as there's a trade-off between position and momentum, there's a trade-off between energy and time. The more precisely you know a particle's energy, the more uncertain you are about when it has that energy. And the more precisely you pin down a moment in time, the more uncertain the energy is. This has some wild consequences. One of them is that empty space isn't empty. Think about that. If you take a perfect vacuum, remove everything, every atom, every photon, every scrap of matter and radiation, you might think you're left with nothing. But the energy-time uncertainty principle says otherwise. If you look at that vacuum over a very, very short time interval, the energy is uncertain. It's fuzzy. And that fuzziness means that energy can briefly fluctuate away from zero. Particles can pop into existence. Matter and antimatter pairs appearing out of nothing, existing for a fleeting instant, and then annihilating each other and vanishing again. These are called virtual particles, and they're constantly bubbling into and out of existence in the vacuum of space, everywhere, all the time. This isn't speculation. It's been confirmed experimentally. There's an effect called the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948. If you put two uncharged metal plates very close together in a vacuum, they feel a tiny attractive force pushing them together. This force comes from the virtual particles, more precisely, from the quantum fluctuations of the electromagnetic field. The plates restrict which fluctuations can exist between them, which creates an imbalance of pressure, and the plates get pushed together. It's been measured. It's real. The vacuum is fizzing with energy, and the uncertainty principle is the reason. And think about what that means for the space around you right now. The air in your room, the gaps between the atoms in the walls, the emptiness between the stars. All of it is seething with quantum fluctuations. The vacuum isn't empty. It's the most complex and dynamic thing there is once you look closely enough. And it's the uncertainty principle that makes it so. But let me come back to something I mentioned earlier, because it's important and I don't want to let it slip by. I said that the uncertainty principle is not about measurement disturbance. Let me explain what I mean by that, because there's a famous thought experiment that Heisenberg himself came up with, and it's both very useful and slightly misleading. Heisenberg imagined what he called a gamma-ray microscope. Suppose you want to measure the exact position of an electron. To see something, you need to bounce light off it. And to see something very small, you need light with a very short wavelength, because the wavelength sets the limit on how small a detail you can resolve. So to see an electron precisely, you need light with an extremely short wavelength, gamma rays. But here's the problem. Gamma rays carry a lot of energy. Each gamma ray photon hits the electron like a tiny cannonball, and it kicks the electron, changing its momentum in an unpredictable way. So the act of measuring the position precisely has disturbed the momentum. You've gained information about where the electron is, but you've lost information about how fast it's going. This is a nice illustration, and it captures the spirit of the uncertainty principle, but it can mislead you into thinking the problem is the photon. That if only you could find a gentler way to look, some non-invasive method of observation, you could beat the uncertainty. And you can't, because the uncertainty isn't caused by the measurement. It exists before the measurement. The electron doesn't have a precise position and a precise momentum waiting to be discovered. Those properties literally do not coexist. This is one of those places where quantum mechanics parts company with everything your brain evolved to handle. In the everyday world, objects have properties whether you're looking at them or not. Your car is in the driveway even when you're not watching it. The moon is there even when nobody's looking at it, as Einstein once complained. But in quantum mechanics, certain properties of a particle only become definite when they're measured. Before measurement, the particle exists in what's called a superposition, a combination of all the possible values, and the measurement forces it to choose one. Not because the measurement reveals a pre-existing fact, but because the measurement creates the fact. Einstein hated this. He spent decades trying to prove that quantum mechanics was incomplete, that there must be hidden variables, secret properties that particles really do have, that would restore the deterministic world he loved. He and Bohr argued about this for years, in person and through letters, in what became one of the greatest intellectual debates in the history of science. Einstein would come up with a clever thought experiment designed to show that you could, in principle, know both position and momentum simultaneously. And Bohr would stay up all night, pacing, agonizing, and come back the next morning with a rebuttal that showed Einstein's argument had a flaw. The most famous of these exchanges happened at the Solvay Conference in 1927, and again in 1930. At the first one, Einstein proposed a thought experiment involving a particle passing through a slit. He argued that by measuring the recoil of the slit, you could determine the particle's momentum without disturbing its position. Bohr showed that accounting for the uncertainty principle in the slit itself, which is also a physical object subject to quantum mechanics, closed the loophole. At the second Solvay conference, Einstein came back with something even cleverer, a thought experiment involving a box of light and a clock, designed to violate the energy-time uncertainty relation. And Bohr, after a sleepless night, demolished it using Einstein's own general relativity, showing that the gravitational redshift introduced exactly the right amount of uncertainty to preserve the principle. These debates were historic, and they were deeply personal. Einstein and Bohr respected each other enormously, even loved each other in a way, but they fundamentally disagreed about the nature of reality. Einstein believed the universe was deterministic, that God does not play dice, as he famously put it. Bohr replied, "Einstein, stop telling God what to do." And here's the thing, as far as we can tell, Bohr was right. Every experiment ever performed has confirmed the uncertainty principle. No hidden variables have been found. Quantum mechanics, with all its strangeness and all its fuzziness, appears to be the correct description of reality at the most fundamental level. The universe really is probabilistic. Outcomes really are uncertain. And the uncertainty isn't ignorance, it's the fabric of nature. But I promised you I'd explain why the universe depends on this, why uncertainty isn't just an interesting fact about physics, but the reason anything exists at all. And to see that, we need to talk about atoms again. Remember the problem that plagued Rutherford's atomic model? Electrons orbiting a nucleus should spiral inward and crash, releasing their energy as radiation, and atoms should collapse in a fraction of a second. Classical physics demanded it, and we know that doesn't happen. But now we can see why. The uncertainty principle prevents it. Imagine an electron in an atom. It's attracted to the positive nucleus by the electromagnetic force. Left to its own devices, the classical electron would fall straight in, spiraling closer and closer, losing energy, until it merged with the nucleus. But quantum mechanics says the electron is a wave, and if you try to confine that wave to a smaller and smaller space, closer and closer to the nucleus, the uncertainty in its position decreases. And when the uncertainty in position decreases, the uncertainty in momentum must increase. The electron gets faster, more energetic. And that increased kinetic energy pushes back against the electromagnetic attraction, preventing the electron from getting any closer. There's an equilibrium, a balance point. The electron settles at a distance where the attraction toward the nucleus is balanced by the quantum pressure from the uncertainty principle. And that distance is the size of the atom, not a random number, a calculable, predictable size determined by the mass of the electron, the charge of the proton, and Planck's constant, the Bohr radius, about 53 trillionths of a meter. And this is why atoms have the size they do. Not because of some arbitrary choice by nature, but because of the uncertainty principle. The fuzziness of quantum mechanics literally holds atoms open. Without it, all matter would collapse to a point. Think about that. Every atom in your body, in the bed beneath you, in the walls around you, in the air you're breathing, exists at the size it does because the uncertainty principle won't let electrons get any closer to the nucleus. You are held together by uncertainty. The solidity of everything around you, the structure of chemistry, the integrity of molecules, all of it rests on the fact that particles can never have a perfectly defined position. The fuzziness isn't a flaw. It's the architecture of reality. And it doesn't stop there. The uncertainty principle doesn't just keep atoms from collapsing. It also makes the stars shine. Let me tell you about quantum tunneling, because it's one of the most beautiful and counterintuitive consequences of the uncertainty principle. And without it, the sun would be dark and the night sky would be empty. Here's the setup. The sun generates energy by nuclear fusion. Deep in its core, where the temperature is about 15 million degrees and the pressure is immense, hydrogen nuclei, which are just individual protons, fuse together to form helium. This process releases energy, a lot of energy, and that energy eventually works its way to the surface and radiates out as sunlight. The warmth on your face on a sunny day, the light that makes plants grow, the energy that drives the weather, all of it comes from nuclear fusion in the sun's core. But here's the problem. Protons are positively charged, and positive charges repel each other powerfully. To fuse two protons together, you need to push them close enough that the strong nuclear force, which is attractive but only works at very short range, can grab them. But first, they have to get through the electromagnetic repulsion, the Coulomb barrier, which is like an energy wall between them. And when physicists calculated how much energy the protons in the sun's core actually have, they found something disturbing. The protons aren't energetic enough. The temperature is too low. The protons are moving too slowly to overcome the Coulomb barrier. They don't have enough energy to climb the wall. If classical physics were the whole story, the sun could not shine. The protons would bounce off each other, repelled by their electric charges, and fusion would never happen. The sun would be a cold, dead ball of hydrogen gas, and every other star in the universe would be the same. No starlight, no warmth, no life. But quantum mechanics saves the day. Because the uncertainty principle means that a particle's position and momentum are fuzzy, and that fuzziness has a remarkable consequence. There's a small but non-zero probability that a particle can appear on the other side of an energy barrier that it classically shouldn't be able to cross. It doesn't go over the barrier, it doesn't go around it, it goes through it. We call this quantum tunneling, and it happens because the wave function of the particle doesn't stop at the barrier. It extends through it, decaying exponentially, and if the barrier is thin enough, a little bit of the wave function pokes out the other side. And that little bit represents a probability, a chance, that the particle will be found beyond the barrier. For any individual pair of protons in the sun's core, the probability of tunneling through the Coulomb barrier is incredibly small, absurdly small. But there are an incomprehensible number of protons in the sun's core, and they're bumping into each other billions of times per second. So even though each individual collision has only a tiny chance of resulting in fusion, the sheer number of collisions means that fusion happens constantly. About 4 million tons of hydrogen is converted into helium every second in the sun's core. 4 million tons every second. And it's all thanks to quantum tunneling, all thanks to the uncertainty principle. This is one of my favorite things in all of physics. The warmth of sunlight, the thing that makes Earth habitable, the thing that allows life to exist, depends on the fact that particles don't have definite positions. If the universe were classical, if particles always had exact locations and exact speeds, if there were no quantum fuzziness, then tunneling would be impossible, fusion wouldn't happen, and the stars would be dark. There would be no light in the universe, no warmth, no life. The uncertainty principle isn't just some abstract rule about subatomic particles. It's the reason the stars shine. It's the reason you can see. Let me sit with that for a moment, because I think it deserves a moment. You're lying there. Maybe your eyes are closed, maybe the room is dark, and even if it is, there's a star out there, 93 million miles away, that has been burning for 4.5 billion years, pouring light and warmth into space. And the only reason it can do that is because of quantum uncertainty. Because particles are fuzzy. Because nature doesn't allow perfect precision. The most important source of energy in your life, the sun, runs on the same principle that makes it impossible to know exactly where an electron is. And that's not a coincidence. It's the same physics. The same fundamental fuzziness, doing different things at different scales, but always rooted in the same beautiful, strange law. Now, quantum tunneling shows up in other places too. A lot of places, actually. It's the reason certain radioactive atoms decay. An alpha particle inside a nucleus doesn't have enough energy to escape the nuclear binding force, but it tunnels out anyway. The probability is low, which is why some radioactive elements have half-lives of billions of years. The tunneling happens, on average, only very rarely for each individual nucleus. But when it does happen, you get radioactive decay, and that radioactive decay is what heats the interior of the Earth, keeps its core molten, drives plate tectonics, and generates the magnetic field that shields us from cosmic radiation. So quantum tunneling doesn't just light the stars, it keeps our planet geologically alive too. And then there's technology. The flash memory in your phone, quantum tunneling. Electrons tunnel through a thin insulating barrier to get trapped on a floating gate, and that's how information gets stored. The tunnel diode, quantum tunneling. Scanning tunneling microscopes, which can image individual atoms on a surface. Quantum tunneling. You've been carrying quantum tunneling in your pocket every day, scrolling through social media with it, taking pictures with it, using it to navigate and communicate, and do everything a modern smartphone does. The technology of the 21st century is built on the uncertainty principle. But let me come back to the deeper story, because there's more to say about what the uncertainty principle tells us about the nature of reality. And to get there, I want to talk about one of the most famous experiments in all of physics, the double-slit experiment, because it demonstrates the weirdness of quantum mechanics more directly, more viscerally, more undeniably than almost anything else. Here's the setup. You have a barrier with two narrow slits in it. You fire particles, let's say electrons, at the barrier, one at a time. On the other side of the barrier, there's a screen that records where each electron lands. If electrons were just particles, little bullets, you'd expect to see two bands on the screen, one behind each slit. Each electron goes through one slit or the other, hits the screen, and over time you build up two clusters of hits. But that's not what happens. What happens is an interference pattern, alternating bands of high and low intensity, bright and dark stripes, exactly the pattern you'd get if waves were passing through both slits and interfering with each other, just like water waves do when they pass through two openings in a breakwater. Peaks reinforcing peaks, troughs canceling peaks. A wave pattern. So the electrons are behaving like waves. Okay, That's consistent with de Broglie. But here's the truly weird part. You're sending the electrons one electron at a time, through the apparatus. Each electron arrives at the screen as a single dot, a definite hit at a definite location. That looks like a particle, but as more and more electrons accumulate, dot by dot, the interference pattern slowly builds up. The pattern of many individual particle-like hits is a wave pattern. How can a single electron interfere with itself? It's only one electron. It can only go through one slit, right? Well, no. In quantum mechanics, the electron goes through both slits simultaneously. Its wave function passes through both openings and interferes on the other side. The electron doesn't take a definite path. It takes all possible paths at once, and the probabilities are determined by the interference of all those paths. And here's where it gets really strange. If you try to determine which slit the electron went through, if you put a detector at one of the slits to catch the electron in the act, the interference pattern disappears. You see the two-band pattern you'd expect from particles. The act of determining which path the electron took forces it to take one definite path, and the wave behavior vanishes. This is not about the detector disturbing the electron. You can make the detection very gentle, as non-invasive as possible. It doesn't matter. The mere act of gaining information about which slit the electron passed through destroys the interference pattern. It's as if the electron knows it's being watched and adjusts its behavior accordingly. Richard Feynman, one of the greatest physicists of the 20th century, and certainly one of the most colorful, said that the double-slit experiment contains the only mystery of quantum mechanics. He was being a bit dramatic, but he had a point. Everything strange about the quantum world, superposition, uncertainty, the role of measurement, the collapse of the wave function, all of it is encapsulated in this one experiment. If you can understand why the electron goes through both slits, and why observing it changes its behavior, you've grasped the core of quantum mechanics. And what does this have to do with the uncertainty principle? Everything. The interference pattern arises because the electron's position is uncertain. It genuinely does not go through one slit, it goes through both. Its wave function spreads through both openings, and the two parts of the wave function interfere. If you force the electron to have a definite position, if you determine which slit it went through, you collapse the wave function, you destroy the superposition, and the interference vanishes. The uncertainty in position is what allows the wave behavior. Take away the uncertainty, and you take away the quantum magic. This is a profound connection. The uncertainty principle isn't just a constraint on what you can measure. It's connected to the deepest features of quantum mechanics: superposition, wave-particle duality, the role of observation. They're all facets of the same underlying truth, which is that nature, at its most fundamental level, is not made of definite things with definite properties. It's made of probabilities, amplitudes, possibilities. And those possibilities only become definite realities when something forces them to, when a measurement is made, or when the particle interacts with its environment in a way that leaves a record. Let me take a breather here and tell you about the man who put all of this into a beautiful mathematical framework: Erwin Schrödinger. He's famous for his cat, of course, that thought experiment about a cat in a box that's supposedly both alive and dead at the same time. We'll get to the cat. But first, let's talk about his equation. In 1926, Schrödinger, an Austrian physicist with a love of mountains and an unconventional personal life, found a wave equation for quantum mechanics. Heisenberg had built his matrix mechanics, which was powerful, but abstract and hard to visualize. Schrödinger wanted something more intuitive. He was inspired by de Broglie's wave idea, and he asked a natural question. If particles are waves, What equation governs those waves? Every type of wave in physics has a wave equation. Sound waves, water waves, light waves, they all obey specific mathematical equations that describe how the waves evolve over time. What's the wave equation for matter waves? Schrödinger found it, and his equation is, to this day, one of the most important equations in all of science. It describes how the wave function of a quantum system evolves over time. Given the wave function at one moment, the Schrödinger equation tells you what it will be at any future moment. It's deterministic, actually, which is funny. The wave function itself evolves in a perfectly predictable way. The randomness only enters when you make a measurement, and the wave function collapses to a definite value. And the wave function is a strange beast. It's a mathematical function, often a complex valued function, meaning it involves imaginary numbers based on the square root of -1. You can't directly observe the wave function. What you can observe is its absolute square, which gives you the probability density, the probability of finding the particle at each location in space. But the wave function itself, with its phases and its complex amplitudes, is where all the quantum magic lives. The interference in the double-slit experiment comes from the phases of the wave function. The uncertainty principle emerges from the mathematical properties of the wave function. Everything important happens in this invisible, unobservable mathematical object that somehow encodes the full reality of a quantum system, which raises a philosophical question that has haunted physics for a century. Is the wave function real? Is it an actual, physical thing, a genuine feature of the world? Or is it just a mathematical tool, a calculation device, a way to organize our knowledge about probabilities without being a thing in itself? This question is still debated today. The Copenhagen interpretation, associated primarily with Bohr and Heisenberg, says the wave function is a tool for prediction, not a description of reality. The many worlds interpretation, proposed by Hugh Everett in 1957, says the wave function is the fundamental reality, and every possible outcome actually occurs, splitting the universe into branches. There are other interpretations too: pilot wave theory, objective collapse theories, relational quantum mechanics, each with its own answer to the question of what the wave function means. And here's the humbling thing: all of these interpretations make the same predictions for any experiment you could actually do. They differ on what they say about reality behind the experiments, about what's really happening when nobody's looking. But experimentally, they're indistinguishable. So as of right now, we genuinely don't know what the wave function is. We know how to use it. We know it gives stunningly accurate predictions. But its deeper nature, what it says about the fundamental structure of reality, remains one of the deepest open questions in all of science. Now, let me tell you about Schrödinger's cat, because it brilliantly illustrates why the uncertainty principle and quantum superposition are so philosophically unsettling. Schrödinger himself came up with this thought experiment in 1935, and he did it not to celebrate quantum mechanics, but to make fun of it. Here's the setup. You put a cat in a sealed box. Inside the box, there's a tiny piece of radioactive material, a Geiger counter, a hammer, and a flask of poison. If a single atom decays, the Geiger counter detects it, triggers the hammer breaks the flask, and the poison kills the cat. The decay is a quantum event. Before you open the box, the atom is in a superposition of decayed and not decayed. And since the cat's fate is linked to the atom, Schrödinger argued, the cat must be in a superposition too, both alive and dead, until you open the box and look. Schrödinger meant this as an absurdity. Obviously, a cat can't be both alive and dead. So something must be wrong with the idea that quantum superpositions persist at macroscopic scales. And yet, the math says what it says. Scientists have put molecules containing hundreds of atoms into superposition. The question isn't whether superposition happens, it's why we don't see it in everyday life. The modern answer involves something called decoherence. A macroscopic object, like a cat, interacts with its environment. Air molecules, photons, vibrations, in such an overwhelmingly complex way that the quantum superposition effectively gets diluted, lost in the noise of trillions of random interactions. The quantum fuzziness doesn't disappear. It becomes entangled with the entire environment, making it impossible to detect. Your coffee cup does have a wave function, but the uncertainty in its position is so fantastically tiny, far smaller than an atomic nucleus, that for all practical purposes it has a definite position. The quantum world and the classical world aren't different worlds. They're the same world, seen at different scales. And speaking of scales, Planck's constant, that tiny number at the heart of all this, is what sets the boundary. If Planck's constant were zero, there would be no uncertainty principle. Quantum mechanics would reduce to classical mechanics, and the universe would be Newton's clockwork. But Planck's constant isn't zero, and that tiny number is what makes atoms stable, makes chemistry possible, makes stars shine, makes life exist. If you could somehow turn a dial and reduce Planck's constant to zero, every atom in the universe would instantly collapse, every star would go dark, and reality as we know it would cease to exist. Now, I want to tell you about a profound challenge to the uncertainty principle that came from Einstein, because it's one of the great stories in physics. In 1935, Einstein published a paper with Boris Podolsky and Nathan Rosen, the EPR paper. It presented what Einstein considered a knockout argument against the completeness of quantum mechanics. The argument goes like this. Suppose you create two particles whose total momentum is zero. They fly apart. Then measure the momentum of particle A. Instantly, you know the momentum of particle B, because it must be the negative of A's. You haven't touched particle B. But instead of momentum, you could have measured A's position, which would also tell you B's position through a similar correlation. Einstein's argument was, since you can determine either property of particle B without touching it, particle B must have had definite values of both all along. Quantum mechanics, which says it doesn't, must be incomplete. This was a brilliant argument, and for decades it was considered a philosophical puzzle. How could you ever test whether hidden variables exist? Then, in 1964, John Stuart Bell, working at CERN, did something extraordinary. He found a measurable, experimental difference between a universe with hidden variables and a universe without them. Bell derived an inequality that any hidden variable theory must satisfy, and he showed that quantum mechanics predicts violations of that bound. The experiments have been done many times. The first major test was by Alain Aspect in Paris in 1982. The results sided with quantum mechanics. No hidden variables. The fuzziness is real. The most rigorous tests, the loophole-free Bell tests of 2015, confirmed it decisively. The universe does not have hidden variables in Einstein's sense. The uncertainty principle stands. But Bell's theorem revealed something perhaps even stranger. Entangled particles remain connected in a way that defies ordinary intuition. When you measure one, the result is correlated with the other, even across vast distances. Einstein called it spooky action at a distance. The experiments show the spookiness is real. It doesn't allow faster-than-light communication because the individual results look random. But the correlations themselves are stronger than anything classical physics allows. And at the root of all of this, at the foundation of entanglement and everything that makes quantum mechanics so strange, is the uncertainty principle, the fact that particles don't have definite properties until they're measured. The fact that nature, at its most fundamental level, is not a collection of definite things with definite properties, but a web of possibilities, probabilities, and correlations. I want to slow down for a moment and tell you about some of the people behind these ideas, because the human story is as fascinating as the physics. Werner Heisenberg, who gave us the uncertainty principle, was a complicated figure. He was brilliant, there's no question about that. He was also young. When he formulated matrix mechanics and derived the uncertainty relation, he was in his mid-20s. He won the Nobel Prize at 31. He played piano well enough to have considered a career in music. He loved hiking and skiing, and during the Second World War, he led Germany's nuclear energy program, a fact that has generated decades of debate. Did he deliberately slow the program down? Did he fail because he didn't understand the physics? Or did he simply not have the resources? The evidence is ambiguous, and historians still argue about it. What's not ambiguous is his contribution to physics. The uncertainty principle was his insight, and it's one of the most important ideas ever conceived by a human mind. But Heisenberg was also famously combative and didn't always give credit where it was due. His relationship with Schrödinger was prickly. He and Bohr had a deep intellectual partnership that was sometimes strained by disagreement and, later, by the war. And he quarreled with others, notably Max Born, over who deserved credit for various aspects of quantum mechanics. Born, by the way, deserves more recognition than he usually gets. It was Max Born who realized that the wave function in Schrödinger's equation should be interpreted as a probability amplitude. Schrödinger himself thought the wave function was a real, physical wave, something like a charge cloud. Born said no. The wave function squared gives you the probability of finding the particle at a given location. That's the Born rule, and it's one of the fundamental postulates of quantum mechanics. Born didn't receive the Nobel Prize for this until 1954, nearly 30 years later, a testament to how controversial the probabilistic interpretation was. And then there's Paul Dirac, the English physicist, who was, by most accounts, one of the strangest and most brilliant people to ever live. Dirac was famously taciturn. When a colleague complained about a character in a novel, saying, "The hero is left at the end in exactly the same dilemma that he faced at the beginning," Dirac reportedly said, "What was the dilemma?" He took language literally. He once declined a knighthood because he didn't want to be called Sir, but his physics was transcendent. In 1928, Dirac found an equation for the electron that was consistent with both quantum mechanics and Einstein's special relativity. The Dirac equation was immediately recognized as a masterpiece. It correctly predicted the electron's spin, a quantum property that had been experimentally observed but not theoretically explained. And it predicted something even more extraordinary, the existence of antimatter. The Dirac equation had solutions with negative energy, which didn't make physical sense at first. But Dirac realized that these solutions corresponded to a new kind of particle, identical to the electron, but with a positive charge, an anti-electron. He predicted its existence in 1931, and it was discovered experimentally by Carl Anderson in 1932, using a cloud chamber at Caltech. Anderson called it the positron. It was the first particle of antimatter ever detected, and its existence was a direct consequence of combining quantum mechanics with relativity. And antimatter is intimately connected to the uncertainty principle through the energy-time relation. Remember those virtual particles I mentioned? Matter-antimatter pairs popping into and out of existence in the vacuum. Those are governed by the energy-time uncertainty principle. The shorter their lifetime, the more uncertain their energy, which means they can briefly borrow enough energy to exist. It's as if nature has a credit system. You can overdraw your energy account as long as you pay it back quickly enough. And this quantum credit is what makes the vacuum seethe with virtual particles, shaping the behavior of every force in nature. Speaking of forces, let me tell you about quantum electrodynamics, because it's one of the great triumphs of physics, and it's built entirely on the foundation of quantum uncertainty. Quantum electrodynamics, or QED, is the quantum theory of the electromagnetic force. It describes how charged particles, like electrons, interact with photons, the particles of light. It was developed in the late 1940s by three physicists working independently: Richard Feynman, in the United States; Julian Schwinger, also in the United States; and Shinichiro Tomonaga in Japan. They each found different but mathematically equivalent approaches, and they shared the Nobel Prize in 1965. QED is, by some measures, the most accurate scientific theory ever created. Its predictions match experiments to a precision of about 1 part in a trillion. Let me give you an example. There's a property of the electron called its magnetic moment, which describes how it behaves in a magnetic field. QED predicts this quantity to extraordinary precision, and the experimental measurement agrees to more than 10 decimal places. It's as if you predicted the distance from New York to Los Angeles, and got it right to within the thickness of a human hair. That's the level of agreement between QED and experiment. And how does QED work? Through virtual particles, through the uncertainty principle. When two electrons interact, they don't push each other directly. Instead, they exchange virtual photons. Photons that pop into existence, travel from one electron to the other, and disappear, all happening within the time allowed by the energy-time uncertainty relation. These virtual photons are the carriers of the electromagnetic force. Every time you see two magnets repel or attract, every time a light switch works, every time a chemical bond forms, it's virtual photons being exchanged, and the whole process is governed by the uncertainty principle. Feynman developed a beautiful visual language for these interactions, called Feynman diagrams. They look deceptively simple, little lines and squiggles on a page, but each one represents a precise mathematical calculation. An electron emits a photon, another electron absorbs it. The electron emits a photon that briefly becomes a virtual electron-positron pair, which then recombines into a photon. Every possible path, every possible sequence of virtual particle creation and annihilation contributes to the final answer. And to get the right answer, you have to add them all up, an infinite number of increasingly complex diagrams, each one contributing a smaller and smaller correction. This process is called perturbation theory, and it works spectacularly well for QED because the electromagnetic force is relatively weak, which means each successive diagram contributes less than the one before. The series converges, and you can get incredibly precise answers by calculating just the first few terms. Now, Feynman himself was a character. He played bongo drums. He picked locks at Los Alamos during the Manhattan Project. He wrote popular books about physics that are still in print and still wonderful. He was as playful as Dirac was serious, and his lectures are legendary. He once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics," which is simultaneously discouraging and reassuring. But Feynman also contributed something profound to our understanding of quantum mechanics and the uncertainty principle. He developed an approach called the path integral formulation, or the sum over histories. The idea is this: to calculate the probability of a particle going from point A to point B, you don't consider one path or even a few paths, you consider every possible path the particle could take. Every single one. Straight lines, curves, zigzags, loops, paths that go to the far side of the galaxy and back. Every path gets a certain mathematical weight, a complex number called a phase, and you add up all the phases from all the paths to get the total probability amplitude. For most paths, the phases cancel out. They point in random directions, and when you add them up, they average to 0. But for paths near the classical trajectory, the path Newton would predict, the phases all line up, and they add up constructively. That's why macroscopic objects follow classical paths. Not because the other paths are forbidden, but because their contributions cancel out. At the quantum level, the particle takes every path simultaneously. It's only when you add them all up that the classical path emerges. This is the uncertainty principle in disguise. The particle doesn't have a definite trajectory. It takes all trajectories at once. Its position along the way is fundamentally uncertain, and the uncertainty is not a lack of knowledge, it's the actual physics. The particle really does explore every path, and the interference between those paths is what gives quantum mechanics its distinctive character. Let me take you somewhere different now, the smallest scale we can even talk about in physics, because the uncertainty principle has something to say about that too, and it takes us right to the edge of what we understand. There's a length called the Planck length, about 1.6 times 10 to the minus 35 meters. If you took an atom, which is already about 10 to the minus 10 meters across, the Planck length is to an atom what an atom is to the observable universe. And at this scale, the uncertainty principle and gravity collide in a way that nobody fully understands. At the Planck scale, the uncertainty in a particle's position becomes so large relative to the gravitational effects of its energy that the very concept of spacetime breaks down. Space isn't smooth there. It's a roiling quantum foam, fluctuating wildly. This is the regime where quantum mechanics and general relativity come into conflict. General relativity describes spacetime as smooth. Quantum mechanics says the subatomic world is fundamentally uncertain. When you apply both at the Planck scale, the math breaks. You get infinities, nonsensical answers. How to reconcile them is one of the great unsolved problems. String theory proposes that the fundamental entities are tiny vibrating strings, each about the Planck length. Loop quantum gravity proposes that space itself is quantized, made of discrete chunks. Both are speculative and unconfirmed. The honest truth is that we don't yet understand the Planck scale, and the uncertainty principle is right at the center of the mystery. But even without a complete theory, the uncertainty principle has given us remarkable insights. One is Hawking radiation, discovered by Stephen Hawking in 1974. Near a black hole's event horizon, the energy-time uncertainty principle allows virtual particle pairs to pop into existence. Usually they annihilate instantly, but near the event horizon, one particle can fall in while the other escapes, carrying energy away. The black hole slowly evaporates. For a solar mass black hole, this takes about 10 to the 67 years, unimaginably longer than the current age of the universe. But for very small black holes, evaporation would be fast. Hawking radiation raises some of the deepest questions in physics. When the black hole evaporates, what happens to the information about everything that fell in? Quantum mechanics says information can never be destroyed, but evaporation seems to erase it. This is the black hole information paradox, debated for nearly 50 years without resolution. And once again, at the root of it is the uncertainty principle. Let me come at this from another angle. Zero-point energy. In classical physics, the lowest energy of any system is zero. A particle at rest has no kinetic energy, but the uncertainty principle says no. If a particle had zero momentum, its uncertainty in momentum would be zero, which means its position uncertainty would have to be infinite. So there's a minimum, the zero-point energy. Even at absolute zero temperature, particles still jitter, fields still fluctuate. This has a remarkable consequence for helium. Helium is so light that its zero-point energy prevents it from freezing under normal pressure. Cool it all the way to absolute zero, and it remains liquid. The quantum jittering won't let the atoms lock into a solid. You have to apply pressure to freeze it. This is a direct, macroscopic manifestation of the uncertainty principle. And below about 2.2 Kelvin, liquid helium becomes a superfluid. Zero viscosity. It flows without friction, creeps up container walls, passes through the tiniest openings. A quantum phenomenon writ large, where the uncertainty principle and the wave nature of matter combine to create something truly bizarre. Superconductivity is related. In certain metals at very low temperatures, electrons form Cooper pairs that behave as quantum entities, their wave functions spanning the entire material, flowing without resistance. MRI machines use superconducting magnets. Particle accelerators use superconducting cavities. All of it traces back to quantum uncertainty. Let me circle back now to something I touched on earlier, the role of measurement in quantum mechanics, because it raises questions that are genuinely philosophical about what it means for something to exist, what it means to know something. In quantum mechanics, before you measure a particle's position, it doesn't have a definite position. When you measure it, the wave function collapses and the particle is found at a specific location. But what counts as a measurement? Is it the detector? The computer that reads the detector? The human who reads the screen? This is the measurement problem, argued about since the earliest days of quantum mechanics. The Copenhagen interpretation says you shouldn't worry too much about what happens between measurements. Quantum mechanics tells you probabilities of outcomes, and that's all a theory needs to do. Many physicists find this unsatisfying. It seems to privilege the observer in a way no other theory does. The many worlds interpretation, proposed by Hugh Everett III in 1957, takes a radical approach. What if the wave function never collapses? What if every possible outcome actually occurs in different branches of reality? When you measure a particle and find it at position A, there's another version of you who found it at position B. The universe splits constantly into an ever-growing tree of parallel realities. Everett was so discouraged by the initial reception that he left physics entirely. But in recent decades, many worlds has gained a significant following. There's also pilot wave theory, which restores determinism by saying particles do have definite positions, guided by the wave function. And cubism, which says the wave function is subjective, a description of personal beliefs about measurement outcomes. Each interpretation is consistent with all known experiments. They differ on what they say about reality, not what they predict. And the honest truth is that we don't know which is correct. But they all agree on the uncertainty principle. That's the bedrock. Now, let me talk about something practical, because the uncertainty principle touches your life every day. Semiconductors. The transistor, the building block of every computer, phone, and digital device, is a quantum mechanical device. In silicon, electrons occupy energy bands, with a gap between them, the band gap. The existence of these bands is a quantum phenomenon arising from the wave nature of electrons in the crystal lattice. If electrons were classical particles, there would be no semiconductors, no transistors, no computers, no phones, no internet. The entire digital revolution depends on quantum mechanics. Every text message, every web search, every streaming video runs on transistors, and transistors are quantum mechanical devices. Lasers are quantum mechanical. MRI machines use quantum properties of nuclei. LED lights emit through quantum processes. GPS atomic clocks depend on quantum energy levels. You are surrounded by quantum mechanics, and the uncertainty principle, far from being a limitation, is the enabling feature. Without quantum uncertainty, without wave behavior and discrete energy levels and tunneling, none of this technology would work. We'd be stuck in the 19th century, and the scanning tunneling microscope, invented by Gerd Binnig and Heinrich Rohrer at IBM Zurich in 1981, uses quantum tunneling to image individual atoms. You bring a sharp tip very close to a surface, apply a voltage, and electrons tunnel through the gap. The tunneling current depends exponentially on the distance. By scanning and measuring current, you build an atomic resolution map. In 1989, Don Egler at IBM used one to arrange 35 xenon atoms to spell IBM, moving atoms one at a time with atomic precision made possible entirely by the uncertainty principle. Let me take you to the stars now, not metaphorically, literally, because the uncertainty principle shapes the lives and deaths of stars in ways that are almost poetic. We talked about how quantum tunneling makes nuclear fusion possible in the sun's core, but the uncertainty principle does much more than that. It determines the entire life cycle of a star, from birth to death, and the remnants it leaves behind. A star is born when a cloud of gas, mostly hydrogen, collapses under its own gravity. As it collapses, the gas heats up, and eventually, the core gets hot enough for nuclear fusion to begin. The fusion produces energy, which creates pressure, which pushes outward against the inward pull of gravity. The star reaches an equilibrium, a balance between gravity and radiation pressure, and it shines. Now, there are actually several stages of fusion that a star goes through, depending on its mass. Our sun fuses hydrogen into helium. That's enough to sustain it for about 10 billion years, and it's currently about halfway through its life. But more massive stars can fuse heavier elements. After hydrogen, they fuse helium into carbon and oxygen, then carbon into neon and magnesium, then oxygen into silicon and sulfur, and finally silicon into iron. Each stage requires higher temperatures, because heavier nuclei have more protons and therefore stronger Coulomb barriers. Each stage is shorter than the last, because the energy yield decreases. And every single one of these fusion reactions, without exception, depends on quantum tunneling. The temperatures inside stars, even the most massive and hottest stars, are never high enough for nuclei to classically overcome their mutual repulsion. Every fusion reaction in every star in the universe relies on the uncertainty principle to allow nuclei to tunnel through barriers they classically can't cross. If you could somehow turn off quantum mechanics, every star in the universe would go dark. Instantly. When a massive star reaches iron, fusion stops. Iron is the most tightly bound nucleus, the bottom of the energy curve. Fusing iron doesn't release energy, it consumes it. With no energy source to support it, the core collapses catastrophically in about a quarter of a second, triggering a supernova, one of the most violent events in the universe. And what's left behind? If the core isn't too massive, you get a neutron star, a ball of neutrons, roughly the mass of our sun, but crammed into a sphere about 20 kilometers across. A teaspoon of neutron star material would weigh about 1 billion tons. The density is almost incomprehensible, And here's where the uncertainty principle shows up again. A neutron star is supported against gravitational collapse by something called neutron degeneracy pressure. It's a quantum mechanical effect, closely related to the uncertainty principle. The Pauli exclusion principle, formulated by Wolfgang Pauli in 1925, says that no two identical fermions, a category that includes electrons, protons, and neutrons, can occupy the same quantum state. This means that in a neutron star, where the neutrons are packed as tightly as possible, they can't all be in the lowest energy state. They're forced into higher and higher energy states, which gives them more momentum, which creates an outward pressure. This pressure, neutron degeneracy pressure, is what supports the neutron star against the enormous inward pull of gravity. And here's the connection to the uncertainty principle. The Pauli exclusion principle and the uncertainty principle are deeply related. The exclusion principle is a consequence of the antisymmetric nature of fermion wave functions, and the momentum of the squeezed fermions is a direct consequence of the position-momentum uncertainty relation. When you confine neutrons to a very small space, their position uncertainty is small, which means their momentum uncertainty is large, which means they're moving fast, which means they exert pressure. It's the same physics that keeps atoms from collapsing, just at a much more extreme scale. If the core of the collapsing star is too massive, even neutron degeneracy pressure can't hold it up. Then nothing can stop the collapse. Not any known force, not any quantum pressure, nothing. The core collapses all the way down to a singularity, a point of infinite density, surrounded by an event horizon, a black hole. And we're back to Hawking radiation and the mysteries we talked about earlier. So the uncertainty principle shapes the entire life cycle of stars. It enables fusion through tunneling. It provides the pressure that supports white dwarfs, which are held up by electron degeneracy pressure, and neutron stars. And when even quantum pressure fails, it leads to black holes, where the uncertainty principle and gravity create paradoxes that we still can't resolve. There's something deeply beautiful about this. The same tiny number, Planck's constant, the same fundamental fuzziness at the heart of nature, is responsible for the stability of atoms on the smallest scales and the behavior of stars on the largest scales. The quantum and the cosmic aren't separate domains. They're the same physics, playing out at different scales. And let me tell you about one more cosmic connection: the large-scale structure of the universe, the distribution of galaxies and galaxy clusters across the cosmos, traces back to quantum fluctuations in the early universe. During the first fraction of a second after the Big Bang, the universe went through a period of incredibly rapid expansion called inflation. During inflation, tiny quantum fluctuations, fluctuations governed by the uncertainty principle, were stretched to cosmic scales. These fluctuations became the seeds of all the structure we see today. The slight variations in density that, over billions of years, grew into galaxies, stars, planets, and eventually you and me. The cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the universe, carries a pattern of tiny temperature variations. Those variations match, with extraordinary precision, the predictions of inflationary theory for quantum fluctuations, stretched to cosmic scales. When you look at a map of the cosmic microwave background, you're looking at the imprint of the uncertainty principle, frozen into the fabric of the universe, magnified to the largest possible scale. Think about that. The galaxies exist because of quantum uncertainty. The Milky Way, the solar system, Earth, the bed you're lying on, all of it traces back, through an unbroken chain of cause and effect, to quantum fluctuations in the first moments of the universe. Fluctuations that happened because the uncertainty principle guarantees that energy and density can never be perfectly uniform. There must always be fluctuations, always be a little bit of randomness. And from that randomness, through billions of years of gravity and physics and chemistry and biology, here you are. Let me pause on that, because I think it's one of the most staggering facts in all of science. You are a consequence of the uncertainty principle. Not metaphorically, literally. The quantum fuzziness that prevents a particle from having a definite position is the same fuzziness that seeded the formation of galaxies, that allowed stars to shine, that kept atoms from collapsing, that made chemistry possible, that enabled the formation of molecules and cells and brains. The uncertainty principle isn't just a curious fact about subatomic physics. It's the thread that connects the smallest scales to the largest, the first moments of the universe to this very moment, the behavior of a single electron to the existence of everything you've ever seen or touched or loved. Now, I want to bring you to the frontier, the edge of what we know. Because the uncertainty principle is not just a settled piece of science, a finished chapter in the textbook. It's a living part of ongoing research, and it touches some of the most exciting and puzzling questions in modern physics. One of those questions is about quantum computing. A classical computer stores information in bits, which are either 0 or 1. A quantum computer stores information in qubits, which can be in a superposition of 0 and 1 simultaneously. This means that a quantum computer with, say, 300 qubits can, in some sense, explore 2 to the power of 300 possible states at once. That's more states than there are atoms in the observable universe. The computational power comes from the fact that quantum mechanics allows superposition and entanglement, properties that arise directly from the wave nature of particles and the uncertainty principle. But quantum computing is extraordinarily difficult to implement, precisely because of the fragility of quantum states. Decoherence, the process by which quantum superpositions get smeared out by interactions with the environment, is the enemy of quantum computing. A qubit in a superposition is exquisitely sensitive to any disturbance, any stray photon, any vibration. And there's a deep irony in this. The uncertainty principle is what makes quantum computing powerful, because it allows superposition and entanglement. But the uncertainty principle is also what makes quantum computing difficult, because the quantum fluctuations it generates are a constant source of noise and error. Physicists and engineers are in a constant battle with the uncertainty principle, trying to harness its power while shielding their systems from its disruptive effects. Another frontier where the uncertainty principle plays a central role is in the search for dark matter and dark energy. We know that ordinary matter, everything we can see and touch, makes up only about 5% of the total mass energy of the universe. About 27% is dark matter, something that doesn't emit or absorb light but interacts through gravity. About 68% is dark energy, a mysterious force causing the expansion of the universe to accelerate. One possibility for dark energy, though it doesn't quite work quantitatively, is that it's related to the quantum vacuum energy, the zero-point energy of all the quantum fields in the universe. The energy of the vacuum fluctuations, the virtual particles popping in and out of existence because of the uncertainty principle, should contribute to the expansion of the universe. But when physicists calculate this vacuum energy, they get a number that's too large by a factor of about 10 to the 120. That's been called the worst prediction in the history of physics. The cosmological constant problem sits right at the intersection of quantum mechanics and gravity, right where the uncertainty principle meets general relativity, and nobody knows how to solve it. And then there's quantum cryptography, which uses the uncertainty principle as a security guarantee. You can use quantum mechanics to distribute encryption keys in a way that is provably secure. If an eavesdropper tries to intercept the quantum signals, the uncertainty principle guarantees that their measurement will disturb the signals in a detectable way. Any attempt to spy leaves a trace. The security isn't based on computational difficulty. It's based on the laws of physics. As long as quantum mechanics is correct, the encryption is unbreakable. That's a remarkable thing, using the fundamental fuzziness of nature as a shield. Let me slow down now and talk about something more philosophical, because the uncertainty principle raises questions that go beyond physics, into the territory of philosophy, about the nature of knowledge, the nature of reality, and the relationship between the two. For most of human history, we've assumed that reality has definite properties, that things are a certain way whether we're looking at them or not, and that the job of science is to discover what those properties are. This is called realism, and it's such a natural assumption that most people don't even think about it. Of course the moon is there when nobody's looking at it. Of course electrons have positions. Of course the world is made of stuff. Quantum mechanics challenges this assumption at a fundamental level. If the uncertainty principle is right, and all evidence says it is, then particles don't have definite properties until they're measured. The world isn't made of stuff with definite features. It's made of stuff with possible features, features that become definite only when something forces them to. And what forces them to is measurement, interaction, the entanglement of the system with its surroundings. This is a radical departure from the way we've always thought about the world. And different physicists, thoughtful people who agree on the math and the experiments, give radically different answers about what it means. Some say the question of what's happening between measurements is meaningless. Some say reality is the wave function, with countless parallel worlds branching at every moment. Some say reality is a network of relations, that a particle's properties depend on what it's interacting with. What's remarkable is that all of these views are compatible with the uncertainty principle. The principle itself is robust. It survives every interpretation. It's like a diamond that looks different from every angle but never changes shape. Let me take you to something more concrete. LIGO, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time in September 2015, confirming a prediction Einstein had made 100 years earlier. Gravitational waves are ripples in spacetime, produced by the most violent events in the universe, like two black holes merging. By the time these ripples reach Earth, they're incredibly faint. The distortion they produce is about 1 part in 10 to the 21. That's a change in length of about 1,000th the diameter of a proton. And one of the fundamental noise sources that limits LIGO's sensitivity is the uncertainty principle. The laser light in LIGO is made of photons, and photons obey quantum mechanics. The arrival time of each photon has a quantum uncertainty, shot noise, that's a direct consequence of the uncertainty principle. When photons bounce off the mirrors, they give tiny random kicks, radiation pressure noise, also a consequence of quantum uncertainty. But physicists aren't content with this limit. They've developed techniques to get around the standard quantum limit, using a trick called quantum squeezing. The uncertainty principle says the product of two uncertainties must be at least a certain amount. But it doesn't say the uncertainties have to be equal. You can squeeze one uncertainty smaller at the expense of making the other larger, as long as the product stays above the minimum. LIGO now uses squeezed light to reduce shot noise below the standard quantum limit, increasing its sensitivity and allowing it to detect more distant gravitational wave events. This is the uncertainty principle being used as a tool. Physicists aren't fighting it. They're working with it, reshaping the quantum noise to suit their purposes. And the results are stunning. LIGO with squeezed light can see further into the cosmos, gathering more data about black holes and neutron stars and the most extreme environments in the universe. Let me tell you one more story. It's about biology, which might seem surprising in a narration about quantum physics, but the connection is real and it's fascinating. In recent years, a new field has emerged called quantum biology. It explores the possibility that quantum mechanical effects, including quantum tunneling, play a role in biological processes. This is surprising because biological systems are warm, wet, and noisy, exactly the kind of environment where you'd expect quantum coherence to be destroyed almost instantly. But nature, it turns out, is cleverer than we gave it credit for. One of the most studied examples is photosynthesis. When a photon of sunlight hits a chlorophyll molecule in a plant leaf, it creates an electronic excitation that needs to find its way to the reaction center. For a long time, scientists assumed this was a random walk, a classical process. But in 2007, a team led by Graham Fleming at the University of California, Berkeley, discovered evidence that the process is quantum mechanical. The excitation takes all paths simultaneously, exploring the molecular network as a quantum superposition, finding the most efficient route with near-perfect efficiency. The results are still debated, but the idea that plants have been doing quantum computing for billions of years is tantalizing. The leaf on the tree outside your window might be running quantum algorithms. Another possible example is bird navigation. Some migratory birds can sense the Earth's magnetic field and use it for navigation. The leading theory involves a quantum mechanical process called the radical pair mechanism. When molecules in the bird's retina absorb light, they create pairs with entangled electron spins. The Earth's magnetic field affects the spins, which affects the chemistry, which the bird's brain detects. If this is right, birds literally see the magnetic field using quantum entanglement, and this has been happening for millions of years, long before any human knew quantum mechanics existed. These examples are still being investigated, and not all will necessarily hold up. But the very possibility that life has found ways to exploit quantum mechanics, to turn the uncertainty principle into a biological tool, suggests that the quantum world is not as foreign from everyday experience as we sometimes think. It may be woven into the very fabric of life. And while we're here, let me circle back to the quantum vacuum one more time, because there's a metaphor I love. Classical physics describes the world as a frozen lake, smooth and still and perfectly predictable. Quantum mechanics reveals that beneath the ice, the water is churning. The uncertainty principle is the reason the lake can never truly freeze. There's always motion, always fluctuation, always something happening, no matter how cold and empty things appear on the surface. The vacuum is everywhere. Every cubic centimeter of the air around you, every cubic centimeter of the void between stars, is seething with quantum activity. Virtual particles appearing and disappearing, energy fluctuating, the fabric of reality vibrating at every point. You are immersed in the quantum vacuum. You always have been. Every moment of your life, surrounded by this invisible activity. And it's all because of the uncertainty principle, because the universe, at its most fundamental level, is restless. So let's come full circle now. Let me bring you back to where we started, to the question in the title. Why can you never know exactly where a particle is, and why does the universe depend on it? The first part of the answer is almost deceptively simple once you've followed the journey we've been on. You can never know exactly where a particle is because a particle is not a tiny dot, it's a wave, a spread of possibilities described by a wave function, and the wave function, by its mathematical nature, cannot be both perfectly localized in space and have a perfectly defined wavelength. Since wavelength corresponds to momentum, you can't know both position and momentum simultaneously. The uncertainty is built into what a particle is, but that's the technical answer. The deeper answer is about why this matters, and the answer is everything. The uncertainty principle holds atoms together. Without it, electrons would spiral into nuclei and atoms would collapse. There would be no chemistry, no molecules, no solid matter. The bed beneath you would not exist. You would not exist. The uncertainty principle makes the stars shine. Without quantum tunneling, nuclear fusion would be impossible at stellar temperatures. The sun would be a cold, dark sphere. So would every other star. The universe would be cold and dark. The uncertainty principle shapes the structure of the cosmos. Quantum fluctuations in the early universe became the seeds of galaxies and galaxy clusters. Without uncertainty, the early universe would have been perfectly smooth, and no structures would have formed. The uncertainty principle powers our technology. Transistors, lasers, MRI machines, GPS, nuclear energy, quantum cryptography. All of it depends on quantum mechanics, and all of quantum mechanics depends on the uncertainty principle. The uncertainty principle even plays a role in biology. Photosynthesis may use quantum coherence. Birds may navigate using quantum entanglement. Life itself may have evolved to exploit the very fuzziness that seems, at first glance, like a limitation. So why can you never know exactly where a particle is? Because that's not how the universe works. The universe is not a clockwork. It's not a machine with definite parts in definite positions doing definite things. At its most fundamental level, the universe is a web of possibilities, probabilities, and correlations. Things become definite only when they interact, only when the wave function meets the world. And the fundamental fuzziness is not a bug. It's the operating system. It's what makes everything possible. And I think there's something deeply reassuring about that. We live in a culture that values certainty. The uncertainty principle says there are limits. There are things you cannot know, not because you're not trying hard enough, but because the universe is built that way. And those limits are not constraints on our ambitions. They're the source of our existence. Think about that as you lie there. Every atom in your body is a testament to the uncertainty principle. The stability of those atoms, the bonds holding your molecules together, the proteins making your cells work, the neurons producing your thoughts, all of it depends on quantum uncertainty. The warmth around you comes from a star, powered by quantum tunneling. The light from any screen or lamp near you is made of photons, each carrying a definite amount of energy, but arriving at slightly random times, because the uncertainty principle won't allow perfect regularity. You are a quantum creature, made of quantum parts, living in a quantum universe. And the thing that makes this universe possible, the thing that keeps it from collapsing into a featureless, lifeless state, is the simple, profound fact that you can never know exactly where a particle is. The uncertainty is not the problem. The uncertainty is the point. Let me leave you with a few thoughts to drift off with. Not conclusions exactly, but invitations. We don't know what the wave function really is. We don't know if the many worlds interpretation is right. We don't know how to reconcile quantum mechanics with gravity. We don't know what dark matter is, or dark energy, or why the vacuum energy is so much smaller than our calculations predict. These are not failures of science. They are the frontier. They are the places where the next great ideas will come from. And the uncertainty principle will be there, at the heart of whatever comes next. It has survived every test, every challenge, every attempt to overthrow it. Whatever the next revolution in physics looks like, It will not abolish the uncertainty principle. It will deepen it. There's something Niels Bohr once said that I've always loved. He said that physics is not about how the world is. It's about what we can say about the world. The uncertainty principle is the most honest statement physics has ever made. It doesn't claim to know everything. It tells you, precisely and quantitatively, what can be known and what cannot. And it shows you that the boundary between the knowable and the unknowable is not a wall but a doorway, an opening onto a universe that is richer, stranger, and more beautiful than any clockwork could ever be. You're lying there. Maybe your eyes are closed, maybe you're drifting. The room around you is quiet, but the atoms in your body are humming with quantum activity. The electrons in every atom are occupying their orbitals, those beautiful standing wave patterns, held in place by the uncertainty principle. The protons and neutrons in every nucleus are seething with quarks and gluons, held together by forces mediated by virtual particles that pop in and out of existence faster than anything you could ever perceive. And all of it, every bit of it, is made possible by the same simple, beautiful, irreducible fact. You can never know exactly where a particle is, and the universe depends on it. You are one of the universe's surprises, a particular arrangement of atoms held together by quantum forces, powered by quantum energy, thinking thoughts made possible by quantum chemistry, on a planet warmed by a star that shines because of quantum tunneling, in a galaxy that formed because of quantum fluctuations in the first moments of creation. You are a quantum story from beginning to end, and it's a beautiful one. So as you drift off tonight, let yourself feel the quiet strangeness of it all. The particles in your body, gently uncertain. The stars outside, fusing atoms through quantum tunnels. The vacuum around you, buzzing with virtual possibilities. The whole universe, from the Planck scale to the cosmic horizon, shaped and sustained by the uncertainty principle. You can never know exactly where a particle is, and that's not just okay. That's everything. Good night. Sleep well. And know that the universe, in all its quantum fuzziness, is taking care of itself, just as it always has. The uncertainty will be there when you wake up, quietly holding everything together, as it has since the very first moment, and as it will, for all the moments still to come.